No worries. Okay, we can hear you perfectly. So I think we will just go ahead now.
Okay.
Our first talk for today is from Elenia Pacetti about JADE. Please go ahead.
Okay. So good afternoon, everybody, and thank you very much for this opportunity. It has been really great to learn more about all these amazing codes that are available in the community. So for those of you who don't know me, I'm a postdoc at INAF IAPS in Rome, and today I will be presenting my code, JADE, which is a relatively young code. It has been developed over the past 2 years. And JADE stands for Joint Astrochemistry and Disk Evolution. So as the name suggests, it is a code that simulates the composition and evolution of the environment where planet formation takes place. So just to give you Okay, just to give you a bit of a context, so I'm sure you're all very familiar with this plot that Bert already showed yesterday. These are the radial variations of the carbon over oxygen ratio in the disk from the very famous work by Karin Obrig in 2011. And which shows how the abundance of volatiles in the ice phase increases with the distance from the star when crossing the snow lines. So if we let a planet form in this disk, of course, we can have that growth and migration allow planets to accrete materials, so gas and solids from different compositional regions in the disk. And this leaves chemical signatures in the atmosphere that we can try to reveal. And we already started to do that from the ground and now also from space with James Webb. And we will start to do this more systematically very soon with Ariel. But we all know that this is a very simple representation of the composition of disks. Because from one hand, we know that volatiles are only part of the story. So we have evidence from the solar system that elements are distributed not only in volatiles, but also in refractories and semi-volatile components like the refractory organic carbon. So if we want to have a more realistic representation of the planet formation environment, we should account for these additional reservoirs. And then we all know that disks are not static, so they evolve both physically and chemically. And so we need to adopt an integrated modeling approach to both physics and chemistry. And this is where JADE jumps in. So in the first version of the code, we implemented, so from the physical side, we implemented mass transport in the disk, so the viscous evolution of the gas and advection and diffusion of dust grains, and full implementation of chemical kinetics, so accounting for chemical reactions that take place in the gas phase, on the surface of dust grains, and also gas grain interactions. So the goal of all of this is to couple the outcome of JADE, so the disk composition, with planet formation simulations to build a modeling framework that links the composition of planetary atmospheres to the planet formation history. And the final goal is to identify some testable predictions that we can use for atmospheric characterization studies. So this is a scheme of the code. JADE is a 1D code that follows an operator splitting scheme. So at each time step, it evolves the chemistry and then updates the physical structure of the disk and uses the updated parameters to reinitialize the next chemical step. And the chemical module has been developed in collaboration with Catherine using her chemical model, while the physical module has been developed in collaboration with Kees Dallemond using his Disk Lab package. So zooming into the chemical module, So basically, the chemistry takes as input a compositional model of the disk. So we can give as input to the code the partition of elements in refractory volatiles and refractory organics, and then the code, the chemical kinetics solve the chemistry of the volatile component. So using again a full implementation of chemical kinetics, so solving a system of ordinary differential equation for each chemical species included in the model. And this is done with Catherine's model. And this is a typical output of this first step of the iteration. So the code returns the radial abundance profiles of all the molecules included in the model, the volatile molecules included in the model at each time step. Then for the physical module, we implemented the viscous evolution following the classical alpha prescription, and we initialize a surface density using the classical treatment by Linde-Belle-Pringle. And then we solve the viscous evolution and the dust transport following the treatment by Thiel, Birsel from 2010, which is implemented into Disk Lab. And so we solve the viscous evolution of the gas and the advection and diffusion of the dust species. And the code also updates at each time step the mid-plane temperature and the ionization rate. So I will use the rest of the talk to show you just a couple of examples of things that we can do with JADE. So these are this is an example of the radial abundance profiles at the end of a simulation. This is a simulations of 3 million years of evolution, where we investigated 3 disks with 3 different grain sizes. And this is a scenario that reproduces one of the scenarios that Christian Eistrup investigated in his paper from 2016. So this is the reset, the scenario that is called the reset high in Christian's paper. So it's a disk that where we assume that the chemistry underwent a chemical reset, so all molecules are dissociated and then recombined together under high ionization conditions. And so this is a typical output of chemical kinetics coupled with the mass transport in the disk. And so here you can see the contribution to carbon in the solid phase, normalized to the stellar carbon. And here you can see that as the grain size increases, the radial drift becomes more efficient, and then you have that the dust grains pile up at the snow lines and drift inwards and pile up at the snow lines. And then if you see what happens in the gas phase, you have that when the ices sublimate, they enrich the gas phase. So this is the effect that Bert showed yesterday when he was talking about ChemComp. And in this particular example, we actually found that even when we consider grains that are sub-millimeter in size, we can still already have significant enrichments in the gas phase. And of course, this will have the strongest impact in planets that accrete their envelope. So they start the runaway gas accretion phase in this enriched region. And this is just to show you that, of course, from the elemental abundances, we can also compute the elemental ratios in the disk. This is the example for the C over O ratio in the same chemical scenarios that I showed you before. But of course, we can do the same with all the elements, all the chemical species included in the model. And so to sum up, so JADE is a code that simulates the evolution of the composition of the planet formation environment, going beyond stationary models that consider chemistry as static during the planet formation and only based on the ice line chemistry. And the code at the moment implements chemical kinetics and 1D viscous evolution of the gas and radial drift of the dust. And the idea is to couple the output of JADE with planet formation simulations, and you will hear more about these planet formation simulations in the next 2 talks by Diego and Danai. And the code is not publicly available, but we are available for collaborations, and there is an ongoing collaboration within the aerial science team. We are carrying out some modeling works in preparation for the mission launch. And there is also a paper that is about to be submitted, which contains first application of JADE. And yeah, that's all from my side, and I'd be happy to take questions. Thank you.
Thank you very much for this very nice and very, very clear presentation. The talk is open for questions. So, I mean, so I have a few questions. But no, Maria wanted to ask a question.
I don't know how to raise my hands in the computer. And thank you for these very nice thoughts about JADE. I had a question regarding the science of the grains. Could you consider in this code several sciences of the grains? Because it seems to be that you only consider one case, one specific science. How the result change if you consider a standard distribution of grain science?
Yeah, this is something that is in our to-do list. So at the moment, we do not treat dust growth. For this first analysis, we just fixed one grain size, but I'm already working at a new version of the code that can take as input a distribution of grain sizes. So we will soon be able to treat also multiple grain sizes. And then in the future, we should definitely work also on the implementation of dust growth.
Okay, great. Thank you.
Very, very cool. So I have a question about the runtime of the code. How fast is this?
Well, of course, it depends on the resolution and the time step that you consider in the grid. But as a conservative estimate, I'd say that with our current architecture, we can do a 3 million year evolution in just a couple of days. Yeah, 2 days.
Single core or multi-core?
At the moment, we only parallelize the chemistry, not the physics. Well, not the mass transport, because of course you have the different cells are not independent with each other. So at the moment we only parallelize the chemistry, but we do have plans. We are also we are developing a strategy also to parallelize the dust transport, especially when accounting for different grain sizes. So yeah, it's in the plan.
Ah, cool. No, because it's like the moment you couple it to an n-body code, for example, then it's always the question of like, you know, what dominates your runtime, if it's the n-body or the chemistry, right? And then the moment you're dominated by n-body, it doesn't really matter if you spend like a day or 2 days on the chemistry, right? That's is always the underlying question.
Yeah, you're right. Yeah, Diego will talk about the n-body code in the next code in the next talk.
Cool, but so my understanding is that it's, oh, sorry.
No.
My understanding is that one could basically use this framework and basically put like whatever planet formation simulation one prefers into it, being like pebble accretion, planetesimal, n-body, single body. Is this the idea?
Yeah, the idea. Actually, we have already done it. We're just preparing the paper, but there is a paper. There is my paper from 2022 where we didn't use JADE, but we used a static disk composition, but the idea is essentially the same. So we have at each time step during the planet formation process, we have a composition of the disk, so partition of elements between ices and between solids, not only ices, solids and gas at all times. And we from the n-body simulations, we get the accreted masses of gas and solids at all times, and we use the chemical the compositional model of the disk to decompose these accreted masses into contribution to different elements. And the idea is essentially the same, but with JADE, we will do that at each time step, so following the disk evolution.
Super cool. Are there any other questions? This does not seem to be the case. So thank you very much, Elenia, for the presentation.